So this is the part 3 of the SL-1 story, where we finish up the SL-1 story itself and then go on to look at 2 accidents that have similar problems, and which we'll talk about: 3 Mile Island and Chernobyl. As a preface, you might recall that Control Rod 9 was pulled out precipitously, triggering the steam explosion in the SL-1 reactor. The reason why Rod 9 was pulled up like it was is unknown to this day. All we know is Legg yanked up the rod far too high in a method that required significant strength. We know that the C-clamp had been attached to hold the rod in place for attachment to the drive motor, because it was still attached after the steam explosion. But what if Legg and Burns got confused as to which rod they were working on? Other control rods were known to stick pretty regularly. What if Legg pulled on rod number 9 when he thought he was pulling on one of the other rods and yanked hard on it that it was stuck, and sure that any other rod but number 9 could be safely removed this way? Since we know that Burns must have attached the C-clamp to the control rod they were going to work on, the confusion might have been by Burns, and Legg just used the control rod Burns attached the C-clamp to. So Legg was actually working on a rod he didn't recognize was the wrong one. This is probably not what happened, but it's interesting to think about. To me, anyway. Certainly no official report on the accident says this might be true. Anyway, onward. So it's midnight in Idaho. The ambulance that has transported Richard McKinley's body to the central facility, during which he died, returns to SL-1 to transport any other members of the SL-1 crew that might need it. Meanwhile, a couple of men do a radiation survey along Route 20, Route 26, and in the nearest town, the aptly named Atomic City. Still there, by the way. They find no exceptional radiation on the ground. Perhaps fortunately, the prevailing winds that night are to the southwest, so Atomic City is in no danger of being severely irradiated by airborne radiation. The radiation inside the reactor room is intense, but outside of the radiation absorbed by the men who actually went into the reactor room, the contamination of everyone is relatively low, and decontamination is very straightforward. I should mention that the nurse in the ambulance that took McKinley away from SL-1, Helen Lyson, was subjected to radiation from McKinley's body, which was very radioactive. It measured between 100 and 400 rads per hour on different parts of his body, even after his clothes were removed. We know she put an oxygen mask on McKinley's face, so she must have been close to his radioactive body for the 7 to 10 minutes the ambulance took to get to the CFA hospital. Some tellings of this story say that she gave McKinley mouth-to-mouth resuscitation, but that's not so. The ambulance itself was contaminated with McKinley's body, so we know she was irradiated herself. Radiation in the ambulance is measured at 20 rads per hour at the back bumper, where the stretcher holding McKinley was loaded into the ambulance, and 10 rads per hour on the floor. The driver's area, which had special lead protection, has about 1/8 of a rad per hour. So the driver was in no extra danger. Her clothes were radioactive afterwards, so she was decontaminated like other contaminated personnel. Of all the people contaminated in the SL-1 explosion, she ranks not the most irradiated, but among the most irradiated. Now, also around now, all contaminated personnel from SL-1, which is basically everybody who is there from 9 p.m. to midnight who haven't been decontaminated, are transported to decontamination facilities in groups to either the central facilities area or to another research reactor facility to perform decontamination. From just after midnight to sunrise, not much happens except a testing of radiation levels away from the reactor building. The confusion as to exactly what happened at SL-1 continues. If the reactor had exploded and broken through the containment vessel, there would have been uranium and all sorts of other evil all over the place. But the reactor building is clearly undamaged. At sunrise, the ambulance was returned to the CFA for decontamination, which will be difficult. Around that time, a light plane is sent over and around the SL-1 area. The plane is equipped with air samplers, and except for the presence of iodine-131, a byproduct of fission, which is diluted by the atmosphere and by the winds, there isn't much of anything radioactive at all to be found. Iodine-131 has a half-life of 8 days. The roof of the reactor building is seen to be entirely undamaged. Later analysis will determine that on the roof, the radiation is 20 rads per hour, and mostly that's from the iodine-131 gas that escaped from the reactor room. And over the next 3 weeks, about 50 rads, that is to say 50 rads total, not 50 rads per hour, have been released into the atmosphere. So considering what happened, not much. To remind you, the reactor vessel rests on pillars on the first floor. The top of the reactor vessel is accessible from the second floor, and that's where the 3 crewmen were at the time of the explosion. And above that is the so-called fan room, where fans are placed to try and regulate the temperature in the reactor room, because the reactor gives off lots of heat. Now, above the fan room is the roof, which is simple sheet steel, as are the walls of the building. So we have 3 things known now. The reactor room is intensely radioactive. Building 602, the one next to it, is significantly less radioactive. The further you get away from the reactor room, the less radioactivity is absorbed by the people. Also, the air above the reactor is radioactive, but it's from a radioactive gas, which is part of the fission process and is dispersing. The roof doesn't even have holes in it, so this is just escaping from the edges of where the roof meets the walls. So the steam explosion has been largely contained in the reactor building, even though that's not what it was designed to do. The only thing designed to keep an explosion from spreading is the reactor vessel itself. And since the steam explosion ejected radioactive steam, which quickly condensed into water since the walls of the reactor room would have been very cold indeed, since the outside temperature was below 0. The steam quickly cooled, and the radioactive material that it contained stayed mostly in the reactor room. The force of the steam explosion is what contaminated the 3 crewmen by driving radioactive particles into their skin. We know that the door to the reactor room was blown open, and this is the source of the external radiation when some of the steam escaped, which was carrying radioactive particles. Some of the steam would have followed the path of the stairway from the reactor building to building 602, which I suspect is the source of the radioactivity in 602, and is the reason that the further away you get from the reactor room, the lower the radioactivity is in building 602. And since the explosion in SL-1 was a steam explosion, it quickly lost power once it left the confines of the reactor vessel, and so the roof stayed on. So back to our story. At 9 a.m., people at SL-1 are trying to decide if the reactor is in any danger of exploding again. Remember, they still don't know exactly what exploded. The most likely thing they come up with is to pour boric acid into the reactor. Boron is a good absorber of neutrons, and if the reactor is close to critical, the boron would likely put a stop to it. However, it is decided not to do that it probably won't help, and putting acid into the reactor just might make it mad. At the Central Facilities Decontamination Facility, people are trying to figure out how to decontaminate McKinley's body without heavily contaminating whoever tries to do it. McKinley's clothes are cut off, but as we've seen, his body continues to be very highly radioactive. After a couple hours, they give up trying to come up with a procedure, and in the end, they never do. The radioactive particles are just too numerous and too well embedded into all 3 men's skins. Over the next couple hours, teams of men go into building 602 and 606 to get radioactivity logs and the operator's logs, plus the men's service and medical records. The operator's log shows that of the tasks assigned to the crew, the scheduled partial pump down of the water, which is part of the procedure for attaching the mortars to the control rods, has been completed, but nothing after that. So they were working on the part to attach the control rods to the motors. So once they determine that they won't be able to decontaminate the ambulance, it's driven back to SL-1 to have it somewhere. It'll have one more trip to make, transporting Burns' body without any nurse on board from SL-1 to the central area to be decontaminated. That will be as unsuccessful as it was for McKinley. At noon at SL-1, planning begins to see how to get John Burns' body out of the reactor room. At 7:30 at night, a party goes up to the reactor room and recovers Burns' body. Coming up with a way to get Richard Legg's body from the ceiling is left until later because nobody knows how to do it without subjecting people to lots of radiation. In the end, it won't be until January 9th until Legg's body can be recovered. After that, it'll be months of painstaking work and theorizing to figure out what actually happened at SL-1. As part of the testing, the reactor vessel will be moved out of the reactor building with a crane to examine it specifically for damage and conduct other tests to see what kind of reaction happened to the core. And if it's not a nuclear reaction that happened to the core, what exactly did happen? Well, one more thing. Over the years, a mythology has built up over the SL-1 accident that says that pulling rod number 9 out so catastrophically was actually part of a murder-suicide plot where Legg was killing Burns and himself. Burns, it is said, was a serial cheater on his wife, and there are dark but completely unsubstantiated hints that he might have been having an affair with Legg's wife. There are no more problems with this myth, and which doesn't seem to stop it being believed. So Burns was known to have a tempestuous relationship with his own wife. There's absolutely no evidence that he was sniffing around Legg's wife. Legg himself seems to have had a perfectly happy military family life. So we're supposed to believe that Legg hated Burns so much that he would kill himself, Burns, and McKinley by yanking on that control rod. Now, this is an Army base. There are plenty of guns at the Army base. And it was 1961. You could buy guns by mail. Legg could just go shoot Burns, or even the other way around. And that would be that. Heck, it wouldn't be that hard to make it look like a suicide. And even if there is a love triangle going on, why punish McKinley, who was entirely innocent? Why kill him? The purported source for all this information is a speculative memo written by an AE staffer named Stefan Hanauer in 1970. And that memo doesn't mention SL-1 at all. In the memo, he says that although the AEC should be concerned about a terrorist plot or a Russian-controlled sabotage of nuclear reactors, they should, he said, keep track of the operators themselves. Their psychology, their team dynamics needed to be part of the security on nuclear power facilities, in the same way that they were a factor in the security of missile silos. It would be another 10 years before his memo resurfaced and suddenly was declared to be proof of a love triangle in Idaho. A primary popular source for this myth is William McKeown's 2003 book, Idaho Falls, which says that the love triangle is unsubstantiated and then spends the next 21 pages recounting it anyway. So there's the high points of the SL-1 story. The lessons learned by reactor designers is that no single control rod should ever be able to make a reactor go critical. So nothing like what happened at SL-1 could happen again. The SL-1 project itself was shut down permanently. So now let's look at those two other nuclear accidents. We'll see how the SL-1 accident echoes into both of them. The first is 3 Mile Island in Pennsylvania of the United States on March 28, 1979. The 3 Mile Island event involved the meltdown of the number 2 reactor. Despite the hoopla of the event then and now, the only release of radioactivity was small amounts of gaseous radioactive iodine and krypton. Despite the endless propaganda about it, in the end, the safety systems worked. And despite decades of trying to find any health effects in the surrounding population, none has been found ever. Hi there, NRDC. A little bit on the design. The 3 Mile Island reactors were pressurized water reactors, known as PWRs, whereas the SL-1 and, as we'll see, the Chernobyl reactors are boiled water reactors. 3 Mile Island used water heated in the reactor, which was used to heat a separate supply of water, and that fed the turbines. One big advantage is, as the water in the reactor becomes radioactive, which it does, that water never touches the turbines or anything else outside the reactor and its coolant flow. So there are actually two distinct water systems. Steam from the reactor goes into a heat exchanger, and steam from that, steam to make steam. What can I tell you? The steam in the second system is the one that drives the turbines. This steam leaves the turbines and goes into a cooling system to send it back into the heat exchanger. The heat exchanger water is what uses those huge cooling towers you see near nuclear plants. So that water is not radioactive in the least. So that now cooled water goes back into the heat exchanger. An entirely intended side effect of the heat exchanger is that it condenses the steam from the reactor back into water, which goes back into the reactor. By the way, the water in the reactor acts as a neutron moderator of the reaction, as well as being a source of steam. Around and around it goes. The system running the reactor's cooling water has a backup water supply that injects water into the reactor system if something seems to be wrong with the cooling system. This happens automatically. If anything goes seriously wrong, the system scrams, that is to say, performs an emergency shutdown automatically. A scram is when the control rods are inserted back into the core all at once. Once the reactor has its control rods in it, it still heats the water, and that's one of the reasons that extra water supply is there. If anything goes awry, extra water is immediately available to keep the reactor cool. The worst possible case for all this is if the water that moderates the neutrons falls to a level below the core. And then there's nothing to stop it from heating up higher than you want. So keeping the reactor core covered is a goal. So it all works just fine, except when it doesn't. So what went wrong? A very, very simple design flaw. To see how this small flaw cascaded into the accident, we have to look at some of the automatic systems of the reactor. When the temperature in the heat exchanger goes up, it's a reasonable assumption that the source of that heat, the steam from the reactor, has gotten warmer, because that's what heats the water in the heat exchanger. So you don't have to directly measure the water temperature in the reactor itself. You just watch the effects of that steam in the heat exchanger. So if the temperature in the heat exchanger goes up, the system shuts down as a precaution. So what happened in March 1979 is that the pumps that forced water into the heat exchanger system, but not the reactor system, failed. That kind of failure was foreseen in the design. The reactor's water temperature was not being raised. It's just that the heat exchanger water wasn't being cooled as well because it wasn't moving as fast because the pumps weren't working. But the assumption was that the reactor's water, for reasons yet unknown to the operators, was overheating. So the system automatically scrams, drops control rods into the core. This has stopped the reactor from continuing to raise the temperature of the water going to the heat exchanger. That's what they think. They think that the temperature problem is in the core. So when that happens, a valve opens to let out some of the water in the reactor loop on the presumption that since the reactor doesn't need that much water, this will balance the water that's being added by the safety system that adds water to an overheated reactor. That valve is supposed to open for 10 seconds and is part of the normal scram procedure. If it was necessary in the scram situation to reopen that valve, it could be done. You could balance the water coming in and going. Except the signals in the control room recorded that a signal had been sent to open the valve. The operators assumed that it had opened for 10 seconds and then closed, what it's supposed to do. But the valve didn't obey the signal to close. It stayed open. There was no sensor to say that the valve was open or closed, just that it had received the signal to open and would automatically close. The valve status and the flow of water out the valve was not included in the instrumentation. It was just the presumption was, okay, it's going to open and then it's going to close. But the valve hadn't closed. It stayed open. So water's leaving the reactor system unknown to the operator. There's this leak, if you will, that's going out of the reactor system that nobody knows is happening. So there's less water in the system. Even with that extra source of water, there's water leaving the system that nobody knows about. So the temperature in the reactor starts to rise because the automatic systems that add water to the reactor system don't take into account a continuing leak. That's pretty reasonable, really. If the valve works, everything works. But all the operators see is that the temperature in the reactor is going up. That's all they know. They don't know why. They just see that it's happening. So they misdiagnose and overreact. They know that the pumps to the heat exchanger have failed, but they don't recognize that that has nothing to do with what's going on in the reactor. So there's still water leaving the reactor, which is supposed to be steam, but now, because the reactor is lower powered, it's water and steam. So the pumps pushing the water back into the reactor after it leaves the heat exchanger start to vibrate because there's this thing called cavitation where the steam bubbles are bouncing around inside the water. So those pumps start to vibrate. The operators look at that vibration, don't understand why it's happening, and so they turn those pumps off. The presumption was that the vibrating pumps had nothing to do with anything else, and just turning them off would stop the vibration because they were worried that the vibration might get larger and larger and destroy the pumps. Now, turning off those pumps supposedly would have no effect on the reactor because the reactor was already safe and had a separate supply of water for the emergency. Everything was fine, but the water was not doing what they thought it was. But they didn't recognize that. After all, the system at scram should be safe. All the systems should be in operation, and they weren't. All the systems should handle this problem. It's what they were designed to do, except they weren't because of this one flaw. And that's basically it. No major release of radioactivity, and despite decades of trying to find some, no effects on the public health. Hi there, Sierra Club. When informed about this problem at the reactor, the governor of Pennsylvania overreacted in order that all pregnant women and children within a 5-mile radius of 3 Mile Island should be evacuated because of the danger of radioactivity, which wasn't. Giant traffic jam and general chaos.
Good evening. The people around Harrisburg, Pennsylvania, and the 3 Mile Island nuclear plant were told they can sleep in their own homes tonight.
For many years, there has been a vigorous debate in this country about safety. There has been a vigorous debate in this country about energy power plants. The nation's 72 nuclear energy power plants. What happened early this morning at a nuclear power plant. What happened early this morning at a nuclear power plant.
There could be a sudden, violent enough to blow out the walls of the building. Perhaps violent enough to blow out the debris into the environment. Scattering radioactive debris into...
Did they try to find out what happened? Nah. But even if they had, the company running the reactor didn't know what to tell people because the technical people working on the reactor didn't know what was happening themselves. Meanwhile, the water in the core has fallen below the top of the core, and the core gets really warmer and begins to melt. That's the meltdown. So when the core gets uncovered, there's a reaction in the zirconium hydride tubes that hold the uranium pellets, and they release hydrogen. So suddenly there's this bubble of hydrogen that nobody can figure out why it's there. The operators were worried that this hydrogen would explode and crack the containment vessel. And the news of this got out in bad ways, and everybody thought that the reactors didn't know what they were doing, and that was kind of true. But for the hydrogen bubble, the pressure of the hydrogen bubble itself prohibited any kind of electrolytic production of oxygen. So there could be no explosion. There was hydrogen, but no oxygen. Still with me on all this? Good, because some of this will come up in Chernobyl. Just like in SL-1, an overlooked design flaw caused havoc. In this case, the operators were unable to think beyond the instrument readings in front of them to try and understand what was happening. They kept winding up in situations that supposedly could not happen. And the design of the instruments didn't do them any favors in this regard. There were things happening that should have had an instrument telling you about them that didn't. So let's look at the most famous complete failure, the explosive destruction of a reactor at Chernobyl. Chernobyl reactor number 4 was an RBMK 1000 design reactor, which was in common use in the USSR. The Chernobyl complex had 4 reactors, of which number 4 was the newest. RBMK 1000s are boiled water reactors, just like SL-1. In it, the water is boiled to steam by the reactor core, which is fed directly to turbines, which would generate electricity. And then the water would come back, into the reactor, and around we go. RBMKs had a history of accidents ranging from minor to major, but nothing catastrophic. And RBMKs had the support of the Soviet bureaucracy, which you're probably too young to remember, but the bureaucracy never, ever made a mistake. And if you thought so, hello, Siberia. The water temperature in the reactor was around 270 degrees Celsius. That's to ensure that the steam generated enough energy to drive the turbines. So to keep things from getting out of hand, the water flow in the reactor is at very high pressure, so that no water spends too much time near the core. So that means that the system in normal operation needs high-speed, high-pressure water flow. Our stage is now set. On April 25th, 1986, Chernobyl number 4 was scheduled for a shutdown for maintenance. The system will be slowly powered down, and a careful, complete shutdown, according to established working procedures, would be performed. But in the time before the shutdown, it was decided to attempt to test a new safety system. If the steam to the turbines was interrupted, the pump still needed to run to force water into the core until the emergency shutdown could be done. If the turbines get no steam, there's no electricity to run those pumps. The reactor had very muscular diesel generators to pick up the load and run the pumps, but those took between 45 seconds and 2 minutes to start and supply electricity. The supposition was that the turbines, while they spun down to a stop, could still provide enough power to the pumps to keep them running until the diesel generators began providing electricity. This test is mostly for a single reactor, obviously. If you have 4 reactors and one loses generation, power can be drawn from the other 3 reactors. So testing it at Chernobyl number 4 seemed like a good idea. Oh, I should add that this test has been tried repeatedly on RBMKs around the USSR, including at Chernobyl, and they had always failed. The turbines had not generated enough power to keep the pumps running. But the spin-down system had been improved, they thought, so it was hoped that it would work now. Probably. Maybe. So we have 2 things going on at the same time. Procedures for these 2 things had been carefully worked out, and the shift of reactor crewmen assigned to the task had been thoroughly briefed. The scheduled time for the spin-down test and then the shutdown was 2 p.m. on Friday, April 25th. In preparation for this test, the operators of the reactor have already brought number 4 to half power, around 500 megawatts. We'll see that this is actually below the supposed test parameters, but the operators at Chernobyl thought they knew better than a bureaucrat in Moscow, and so they decided to sort of partially begin the shutdown, just in case. So everything's ready. And then the power controller in Kiev, who outranked the reactor operators, ordered that reactor 4 continue running past the time selected for the test because the factories and other industries needed the power for that day and into the night. You might think that the reason for this is stupid, but is entirely characteristic of the Soviet system. In it, managers and employees of factories and transportation sectors and farming and so on would get bonuses if they could meet their production targets. So they were all hell-bent on doing so. This meant that right before the end of the month, and the 25th was the last Friday in April, which counted as the end of the month, there would be this frenzy of activity to make quota. So now the test and number 4 shutdown are pushed back. The controllers in Kiev eventually decided that number 4 had to generate at least 50% power until 11 p.m., and that was about 500 kilowatts. So we're now up against midnight shift change now. So to get even the barest knowledge of what the midnight shift needs to know must start after shift change, because they weren't there during the briefings. So the test specifies that the power for the reactor is to be reduced to 700 megawatts from the 1,000 megawatts normal operation. And then after the test, there'd be a regular shutdown. So reactor number 4 is already below the power requirements of the test. But the test needs to be run so people can get bonuses It decided to continue and just start at the 500 megawatt level. At 12:28 a.m., the reactor power had suddenly dropped from 500 megawatts to 30 megawatts. The reason for this is a little obscure. One of the operators of the new shift had changed the movement of control rods from local, that is, individual rods, to global, all of them at once, which would be normal for a shutdown. So the next time any rod was moved, they were all inserted into the core. So the power drops to 30 megawatts, which is way below the test parameters and, in fact, way below the value that where you have to continue to a shutdown. Also, lowering the power like that triggers a phenomenon called xenon poisoning. Fission in the reactor creates xenon, and that absorbs neutrons. So it makes it harder to raise power back again until the xenon can be dispersed. And it has a very short half-life. One way you can do that is to raise the temperature of the water, and the xenon will be dispersed faster. Now, this phenomenon has been known since World War II, and so it must have been known to the supervisors at Chernobyl. So the reaction in the core has to be raised higher than you would think to get the power back up somewhere near where you want to run the test. This is known as burning off the xenon. So the deputy chief engineer, who's present at the test, insists that the power of the reactor be raised again, even though xenon poisoning is obviously happening. So that means raising control rods to try and goose up the core reaction. By the end of this process, where the reactor is generating 200 megawatts, still way below all the parameters, of the 211 control rods, the total number is 8. That's way below any operating value in the manuals. And with only 8 control rods, the reactor is basically uncontrollable. You don't have any play in the use of the control rods. This was at the direction of the deputy chief engineer. The shift supervisor didn't want to do it, but he was overruled. So the test began at 1:23 a.m. and 4 seconds. The supply of power to the pumps sending water into the reactor is interrupted, and the turbines begin to spin down. But the electricity the turbines generate as they slow down is not enough. The pumps don't keep up with the reactor heat with only these few rods in it. And so heat begins to rise. 36 seconds later, somebody, presumably the shift supervisor, pressed the emergency scram button, which should have pushed all the control rods back into the core. But that's not what happened. What happened was the control rods froze a few inches into the core. Superheated steam, which is now in the reactor, has triggered a reaction in the graphite tips of the rods, which temporarily caused neutron generation to go up, way up. Now, this is a known phenomenon, but it was assumed that this phenomenon would be transient and the effect of the control rods would quickly overcome this problem. But in this case, that didn't happen. The control rods probably jammed because of the increase of reactor power caused the channels the rods were in to deform. So in the time it took for the graphite of the tips of the rods to enter the reactor vessel, the reactor power went up so quickly that the rods could not be inserted further. And remember, we only have 8 rods left in. We can't control this. Without these extra rods, we can't control this reactor. Just after this happens, one of the operators is in the reactor room and sees the graphite caps for the fuel channels, the tubes holding the uranium, bouncing up and down on top of the reactor. Now, that's not supposed to happen. That's really bad. What it means is that there is superheated steam rising up through not quite as superheated steam in bubbles and smashing into the roof. So now we have the reactor really in a runaway situation. The power in the reactor spikes in less than a second to somewhere above 1,600,000 megawatt, which is about 1,700 times the maximum power the reactor was designed for. You might remember this flash to steam phenomenon in SL-1, and for the same reason. There was not enough control rod activity to control the reactor, and it ran away. So finally, the steam pressure is just too much. And unlike Western reactors, where the reactor vessel is basically one piece, the reactor at Chernobyl had a 1,000-ton steel plate that was bolted to the top of the reactor. But the steam pressure is so high that that plate is blasted off the top of the reactor. That's the steam explosion. There were 2 explosions. When the steel lid was blasted off of the reactor, oxygen and nitrogen, air, rushes into the reactor as steam rushes out. Now, you might remember that at 3 Mile Island, there was this phenomenon of the hydrogen bubble that didn't explode because there was no oxygen. Well, because the top plate has been blasted off and air is rushing in, there is oxygen. And there's an ignition source, the reactor core. So this second explosion is much more powerful than the steam explosion. That explosion blasts graphite blocks from outside and inside the reactor onto the roof of reactor number 3 next door, onto what's left of the roof of reactor 4, and into the surrounding countryside. So fires now break out on the top of reactor 4 and reactor 3. And that graphite is very, very radioactive. So now the reactor is uncovered, dry, that is to say no water, on fire, and spewing radioactive steam, radioactive gases, and just radioactive stuff into the sky. Now, witnesses report that the second explosion, as it blasted through the hole in the roof, was colored blue. This has led some to claim that the second explosion was actually atomic, but the level of refinement in the uranium core, and there was no compression on that core, so it couldn't have reached critical mass, so it's not a bomb. I suspect it's burning cobalt-60. It's a radioactive product of fission. The reason I suspect that is that cobalt-60 burns blue and might have led a blue tint to the fireball, in the same way that additives to gunpowder give fireworks different colors. The story of putting out the fires, evacuating over 100,000 people, and trying to clean up the mess is well known. In the U.S., distrust of nuclear power was shouted out by people who claimed they wanted safe power, but had no idea how to do it. And to this day, except for slogans, they still don't. So now it's sum up time. What went wrong? SL-1 failed because of design flaws and human factors that caused a steam explosion, but did not crack the containment vessel because it was over-engineered, and as it turned out, very wisely. Freedom Island 2 failed because of a single design flaw and poor training and a lack of anyone who could look at the problem directly in front of them to figure out that the assumptions by the operators were really bad ones. What I mean is there was nobody who could look at the whole system and recognize what was wrong because they were looking at little pieces and not recognizing the whole problem. Chernobyl number 4 failed because of systemic design flaws, ignoring parameters of the test, poor training, societal factors that valued quota over safety. In other words, the Kiev people who didn't know anything about the test just ordered the reactor to keep going because that's what you do. And also the midnight crew had no actual understanding of what was going on or why. So what's the moral? There's this thing called failure analysis, which is you look at a system and decide how it might fail. Now, this is not popular amongst bean counters because it costs money, and bean counters like counting their beans. So failure analysis should be done very rigorously and best done by people who are not part of the original design of the system, whatever it is. They should look at not only the hardware of the system, but also the techniques of running it, how well the operators have to be educated as to what's going on, and recognize that failure of behavior in the humans is at least as important as the hardware itself. Now, you'd think this would be obvious, but it's not as obvious as it should be, apparently. Bean counters tell you that it's too expensive to do this sort of analysis, and the people who design the system can figure out the failures of it no problem. Well, bean counters should get stuffed. Bye-bye.